Hi, this project explores a comparative analysis of machine learning techniques on MNIST handwritten datasets. It is divided into three main phases, each using a different method for feature representation: raw pixel data, kernel PCA, and Laplacian eigenmaps. In each phase, we evaluate the performance support vector machines for binary and multi-class classifications, along with unsupervised clustering using k-means and hierarchical clustering. The goal is to understand how different data representations affect the accuracy and interpretability of classification and clustering outcomes, particularly across the digits 2, 3, 4, 5, 6, and 8. For part first of my project, I explored different machine learning techniques using the MNIST dataset. I started with linear and Gaussian kernel SVMs for classifying digits 3 and 8. The results showed that Gaussian SVM performed significantly better, with accuracy jumping from 97% to nearly 99.4%. Next, I extended the classification to 6 digits using two strategies, 1v1 and 1v-all SVMs. 1v1 gave slightly better precision and specificity, making it more effective for multi-class problems. I applied k-means clustering to group digits without labels and found that when the number of clusters matched the number of digits, the results were more meaningful and clear. Lastly, I used hierarchical clustering with both Euclidean and L1 distances. The L1 distances grouped similar digits more tightly, offering better visual representation. For part 2 of the project, I applied kernel PCA to reduce the high-dimensional MNIST dataset and evaluated its impact on various machine learning tasks. I tested it on different components from 10 to 100, and I found out that the classification accuracy using 50 components was around 92.6%. I chose 50 components because it reached a strong classification accuracy of around 92.1% with a good balance between precision and recall. It reduced the data size a lot compared to the original 784 dimensions, saving computation time. It kept enough nonlinear structures for SVM to work well. Using the best setup, that is 50 components, I then applied SVM again for binary classification for digits 3 and 8 and observed high accuracy for both linear and RBF SVM, showing that the reduced data retained more patterns. For multi-class classification on digits 2, 3, 4, 5, 6, and 8, 1v1 and 1v-all SVMs gave similar performance with precision around 56%. I also ran k-means clustering on the reduced data and visualized the clusters along with the closest real data images, finding meaningful groupings at different k values. Finally, the hierarchical clustering with Euclidean and L1 distances was used on a small sample to show clear data similarities. Overall, kernel PCA proved effective in compressing the data while maintaining useful structure. In part 6, in this part, I used Laplacian eigenmaps to reduce the dimensionality of the full MNIST dataset. I first tested the number of components, how it affected the spread of the data, and based on the results, I chose 12 components for the final data. Then I applied SVM to classify digits 3 and 8, where RBF kernel slightly outperformed the linear one, achieving an accuracy of about 96%. For multi-class classification on digits 2, 3, 4, 5, 6, and 8, the 1v-all strategy gave better results than 1v1 in terms of precision and recall. I also performed k-means clustering where different k values gave meaningful groupings and the closest real MNIST images were visualized for each cluster center. Finally, I applied hierarchical clustering using both Euclidean and L1 distances, which gave clear structures and for visual analysis. Across all three representations, we observed that the choice of data transformation plays a critical role in model performance. Using raw pixel data, Gaussian SVM showed higher accuracy while 1v1 SVM better than 1v-all for multi-class classification. So this uses when we applied kernel PCA classification, performance improved more components reaching 92% accuracy while clustering results became more structured and meaningfully. Finally, with Laplacian, we achieved competitive classification performance with clear visual clusters even with reduced dimensionality. Thank you.